Now that you've had a chance to review exponents, we're going to be using that to use a really amazing theorem that's called Euler's Theorem. And it's based on the Euler phi function. So first of all, we're going to review that Euler phi function, remind you what the definition is. Then we're going to state what Euler's theorem is. We're going to give a very brief review of the exponent laws that you saw in the last video. And then we're going to use Euler's theorem to do some mod computations that we wouldn't imagine doing with the tools that we had before Euler's theorem. Alright, so let's suppose we have a positive integer n. Just to remind you that phi of n is the number of integers between 1 and n that are relatively prime with n. So you look at all the integers between 1 and n, count the ones that are relatively prime, whatever number of integers that you have, that is phi of n. So just as an example, let's look at phi of 15, and I'm going to use our indirect way of counting on this one. So what I'm going to do is, instead of counting the numbers that are relatively prime with 15, I'm going to count the numbers that aren't relatively prime with 15. So remember, 15 is 3 times 5, which means we have to toss out all multiples of 3, including 3, 6, 9, and 12. We got to toss out all multiples of 5, which include 5, 10, and 15. And yes, I know that 15 is a multiple of 3 as well, but I included that one with the multiples of 5 instead. But in any case, those are all the ones that aren't relatively prime with 15, or aren't relatively prime. And so the ones that are relatively prime are going to be 15 minus those 7 integers, which gives us 8. Alright, so now I'm going to tell you Euler's theorem, which is, by any measure, an amazing fact. And so what it says is that if you have two integers, a and n, whose GCD is 1, in other words, a and n are relatively prime, then if you take a to the phi of n mod n, you get 1. Right? No matter what a is, as long as its GCD with n is equal to 1. And another way of saying that, if you like congruence instead, is that a to the phi of n is congruent to 1 mod n. And just to show you that, I mean, I'm not just making that up, that it's true. I'm not going to actually prove this to you. If you want a proof, actually, you can ask me about it. I could explain it to you maybe during office hours or something. But let's say you have a equals 7, n equals 15. Notice that those two numbers are relatively prime. And remember that phi of 15 is equal to 8. And let's go ahead and compute 7 to the 8, a to the phi of n, which is 7 to the 8 mod 15. So if we do 7 to the 8 mod 15, well, if we do this using our old-fashioned methods, that 7 to the 8th, if we put those 7s into pairs, we get 49 to the 4th. Then we can divide 15 into 49. It gives us a remainder of 4, so we get 4 to the 4th mod 15. And if we split those 4s into pairs, we end up with 16 times 16. And 16 mod 15 is equal to 1, so that gives us 1 squared, which is equal to 1. So all I did was verify that Euler's theorem works in one particular example, but it turns out it works in every single example. And it is an incredible theorem, just one that you wouldn't expect to be true. But it also, for us, when we're doing cryptography, turns out to be incredibly useful. And actually, even when we're doing mod computations, it's going to be useful. And that's what we're going to do in this particular video and in the activities that go with it. So let's go ahead and do our mod computations. And I want to recall a couple of facts. These are just our old friends, the exponent laws that we reviewed in the last video. A to the b times a to the c is equal to a to the b plus c. And a to the b to the c is equal to a to the bc, b times c, right? Okay, and we're going to use both of those in our mod computations below. All right, so Euler's theorem turns out to be a very powerful tool along with those exponent laws with the mod operation. And to give you an idea, let's go ahead and do a computation that would depress the heck out of you if I gave it to you a couple weeks ago, right? Taking 11 to the 2500 mod 17. Now that looks horrible, right? Even if we did all the factoring and stuff that we did before, still it's just depressing even to look at. However, it turns out by using the Euler's theorem, it's going to be, well, not totally easy, right? But a lot easier than the other methods that we had at our disposal. And I'll show you how. All right, so first of all, I want to note that phi of 17 is equal to 16. 17 is a prime, and you showed that every prime, the phi of any prime is 1 less than that prime, right? So that tells us that 11 to the 16 mod 17 is equal to 1. And that gets us somewhere, but it's actually not just 11 to the 16 we know about. I can do something like 11 to the 32 as well. And 32 is significant because it is 16 times 2. And if I use that second exponential law kind of in reverse, 11 to the 16 times 2 is the same as 11 to the 16 to the 2 power. And since we know that 11 to the 16 is equal to is congruent to 1 mod 17, we get 1 squared is equal to 1. So not only is 11 to the 16 mod 17 equal to 1, but 11 to the 32 mod 17 is equal to 1. And I'm sure you can see where I'm headed here. If we take 11 to any multiple of 16, 11 to the 16 times q, whatever, if where q is some integer, then or a positive integer, then we always going to get 1. And here's how. Right? If I look at 11 to the 16q and again use that second exponent law in reverse, that gives me 11 16 to the q power. 11 to the 16 mod 17 is equal to 1, so we get 1 to the q, which is equal to 1. And that suggests that maybe using some kind of quotient remainder on the exponent, not on the actual number 11 to the 2500, but to the exponent of 2500 will be helpful to us. And when I say quotient remainder, I mean we're going to divide 16 into that 25, right? Because we're interested in multiples of 16 because 16 is phi of 17. All right, so we end up with 2500 equals 16 times 156 plus 4. All right, so let me see. So again, I'm just rewriting this on the next slide just so you don't forget what it is. And now what we're going to do is see if we can compute 11 to the 2500 mod 17. All right, now I'm going to replace that 2500 with 16 times 156 plus 4. And now notice in that exponent that we're adding exponents together, right? We're adding two numbers together in that exponent. And so our first exponent law says we can split those up and multiply them. So we get 11 to the 16 times 156 times 11 to the 4 mod 17. Now, in that previous slide, remember, if we take 11 to any exponent that's a multiple of 16, that's always going to give us 1. So that gives us 1 times 11 to the 4th mod 17, which is the same as just a plain old 11 to the 4th mod 17. And now our exponent went all the way down from 2500, which is horrible, down to 4, which is manageable. Right? So now we can put the 11 into pairs and get 121 times 121 mod 17, 121 squared. The 121 mod 17, you have to do a little bit of arithmetic to figure that one out, but that turns out to be 2. And 2 squared is equal to 4, and then there's our mod. And you can see that just by doing one little quotient remainder with the phi of the phi of 17 and a few minor computations gives us a really easy computation for what otherwise would have been a horrible computation. All right, so I just want to summarize what we did there in a more general context so you can see how you can apply this to some of the problems that you're going to see on the activities. So if you want to compute a to the b mod n, what you might try to do is first look at phi of n, compute phi of n, figure out what that is, and then divide b by that phi of n. And if you do that, you're going to get b equals phi of n times some quotient q plus some remainder r. Then when we take a to the b mod n, you're going to replace that b with the quotient remainder form of b, phi of n q plus r mod n, and then you're going to use the first exponent law to break up the two things that you're adding together in the exponent, a to the phi of n times q times a to the r. You're going to use this. Now we're going to use the second exponent law on that a to the phi of nq to split that one into two exponents. So we get a to the phi of n all to the q power times a to the r. And now we can use Euler's theorem to say that a to the phi of n is going to be congruent to 1, and then when we simplify that, we just get a to the r. Now, I should mention one important thing about the a in this situation is that a has to be relatively prime with n. If it's not relatively prime with n, you're not going to get 1 when you take it to the phi of n power. Anyway, so we get a to the b mod n is the same as a to the r mod n. Presumably, r is a lot smaller number. It certainly was in the example that we did before, and that will help you do the computations more easily. In general, what's going to happen is if you have b congruent to r mod phi of n, then a to the b mod n is equal to a to the r mod n. If you don't want to think of r as the remainder, if you just want to think of it as some number that's congruent to b mod phi of n, then that also works as well. All right, so now I think you're ready for the activities for Euler's theorem. Those are on the PDF file included with this video.